Today we're going to talk more about experiments, specifically about confounds and particular threats to internal validity. The outline for today, we'll talk about threats to internal validity, and then we'll talk a little bit about interrogating null effects. So, moving into threats to internal validity. Nikhil, a summer camp counselor and psychology major, has noticed that his current cabin of 15 boys is especially rowdy. He's heard a change in diet might help them calm down, and so he eliminates the sugar snacks and desserts from their meals for 2 days. As he expected, the boys are much quieter and calmer by the end of the week, after the refined sugar has been eliminated from their diets. Now, it could be possible that this counselor thus is convinced that removing the sugar is actually what resulted in these students or summer camp boys not having as much sort of rambunctiousness or energy that was causing them to be rowdy. Now, while it is possible it was the sugar that was causing it, maybe they just got used to their environment and calmed down after the novelty of a new place wore off. And there would be no way really to know from this experimental setup whether it was in fact the sugar that had this effect or maybe something in the environment. Our second example has to do with Dr. Yuki, and she recruits a sample of 40 depressed women, all of whom are interested in receiving psychotherapy to treat depression. She measures their level of depression using a standard depression inventory at the start of therapy, and for 12 weeks, all the women participate in Dr. Yuki's style of cognitive therapy. At the end of the 12-week session, she measures the women again and finds that on the whole, their levels of depression have significantly decreased. Now, at its face, this seems like her style of treating depression is working because on average, these people's depression significantly decreased. But could there have been something that happened in society that resulted in increased happiness levels? Or perhaps simply depression and time are inversely correlated, where as time passes on, levels of depression tend to decrease? How would you know if it is in fact the therapy that affected depression or just something in the environment? Finally, a dormitory on campus has started a Go Green Facebook campaign focused on persuading students to turn out the lights in their rooms when they are not needed. Dorm residents receive emails and messages on Facebook that encourage energy-saving behaviors. At the start of the campaign, the head resident noted how many kilowatt hours the dorms were using by checking the electric meters on the building. At the end of the 2-month campaign, the head resident checks the meters again and finds that usage has dropped. He compares the two measures, the pre-test and the post-test, and finds they are significantly different. Again, at its face, it might seem like this Go Green campaign actually impacted people's electrical usage and they were using less energy. But could it have been that the weather changed? Maybe you went from summer into fall and the use of air conditioners was no longer required, and while no overt behavior actually changed, it looked like there was a decrease in energy expenditure, but that might have been just because of no longer using the energy-intensive air conditioning units as opposed to better practices. Now, the problem that really all three of these have is they don't have any kind of comparison group. You are simply doing something to one group and they're changing, and then one is assuming that is because of the change you implemented. But there's no way really to know because it could have been many other things that resulted in this change that might not have had anything to do whatsoever with the experimenter's manipulation. And so many of the sort of threats to internal validity we're going to talk about can actually be solved just by having a comparison group of some kind. Now, all three of these experiments do not have a comparison group and so would not be considered very good experiments or experiments with a high internal validity. The next type of threats are history threats. These result from some kind of external factor that systematically affects most members of the treatment group at the same time as the treatment itself. Now, this ultimately makes it difficult to know what drove the differences that we saw in our dependent variable. And just to be clear, to be a history threat, the external factor must affect most people in the group in the same direction, and not just a few or in a haphazard way. So what this means is that if you ultimately have some kind of external factor that's randomly affecting people's data, then that random noise is ultimately going to average out and not really cause that much problems. But when you have some kind of external factor that is continually impacting all people of the groups in particular ways, this begins to add a lot of sort of bias to our situations, and it becomes difficult to know how much of our differences are due to those dependent variables and how much are simply due to these other external factors. So a way to look at this, so this relates again to the idea of how many kilowatt hours were used. And so here you can see an effect where there is no true effect of our dependent variable, and it is simply some other factor that is causing our difference. So here you can see a decrease in how much energy is being used, the green line representing the Go Green Facebook campaign, and the orange line representing no campaign. And you can see that both groups start out with a fairly high amount of kilowatt hour usage, and they both decrease as the months go on. And they both decrease in almost exactly the same way. This would indicate that there is really no effect of our Go Green campaign, and rather it is simply just the time of year has changed, resulting in different behaviors of using electricity. However, with this comparison group, if we begin to see these two lines diverge, then we might be able to make inferences about whether our campaign was effective. So here the orange no campaign line shows us that there is a decrease in energy usage, but those people who across the same amount of time also got the Go Green campaign reduced their energy usage even more, thus leading us to be able to now make inferences about the effectiveness of such a Go Green campaign. But notice we could not have done this without having the comparison group, because if this green line was the only line that existed, much like the example given earlier, there would be no way to know how much of this was simply due to the change in year or time or the campaign itself. Next are regression threats. Regression threats are referring to a statistical concept known as regression to the mean. Simply put, regression to the mean ultimately states that if there is an extreme score recorded by an individual or a group, that subsequent scores recorded for the same individual or group are likely to be closer to the mean than the first score. So a way to conceptualize this would be that if you have two parents who are both 7 feet tall, which would be a very extreme score, the chances are that their children are going to be less than 7 feet tall, or slightly closer to the mean. Another way of looking at this would be that if you were able to make 100 free throws in a row at a certain time in your life, chances are out of 100 shots, the next time you go about it, you will score less than 100 free throws. In the reverse, it could also be that you're given 100 chances and you miss all 100 of those free throws. Chances are on the next time you're going to make more than 0 free throws. So ultimately, this concept is true for both positive and negative values. Ultimately, this is referring to the idea that it is very rare to find extreme scores happen repeatedly over time. Now, these kind of threats really only occur when a group is measured twice, because note that ultimately what we're talking about is you will have scores that will approach a mean again if you measure them repeatedly, not that if you only measure it once, because now there's no chance for it to change. Again, these can be managed with valid comparison groups. Now there are a couple different diagrams to look at in this case. So here we can see that we have again two comparison groups. We have depression scores on the y-axis again. The x-axis is showing us the two groups, or pre-therapy and post-therapy. The orange line once more is the therapy group. A green line is no therapy in this case. And so here what we're seeing is that depression scores are relatively high before therapy, and depression scores get lower after therapy. Now, the one for the therapy group ultimately had a greater reduction in their depression scores than the no therapy group. And so what we're assuming here is maybe the average depression scores for everybody are around 12.5, and that people's scores are coming closer over time when they're being measured over and over. And this group here, they are approaching that middle or decreasing more than the no therapy group. And so we could say something like, while there are patterns of regression to the mean, we do see that our therapy group has a greater reduction in depression scores, and thus it's likely our independent variable, or therapy in this case, is having some effect. Now, if your graph looks something like this, where the no treatment group kind of stays steady and the therapy group starts out more extreme at the pre-therapy measurement and then approaches that line at the post-therapy, here it is difficult to say that the therapy actually worked. Because first of all, notice that at the start, our therapy group has higher depression levels on average than our no therapy group. And so just statistically speaking, we could say that these two are likely to approach each other at the next measurement because of the possibility that this measurement right here for the therapy group was an extreme score, and we're likely to see some type of reduction in that extreme. In the case of this, it would be very difficult to know if our therapy is what drove this reduction in depression scores, or if it was simply regression to the mean. Finally, if you see something like this, then it becomes much harder to attribute the differences to regressions to the mean, because notice we have a no therapy group that doesn't really change, so we're assuming this is sort of the average reading, and now we have a therapy group who starts out with higher depression scores than the control group, but at the next measurement after therapy, you see that their new depression scores are even lower than the average for the control group. This would be hard to explain with regression to the mean, because notice it does not say that if you have extreme positive scores, you are now likely to get extreme negative scores. In fact, that is far more unlikely than just moving from a high or low back to the middle. If you have a graph like this, chances are you have found some effect. Also, well, no, that's not important at the moment. Next, we'll talk about attrition threats. Attrition threats refer to the systematic loss of participants from an experimental group. Now, attrition of participants who are at extremes of a group are much worse for our experimental results than if we have attrition of participants who are sort of in the middle of a group in terms of measurement. Now, attrition can be ultimately managed by removing data from incomplete respondents. And while you might think that this is something everybody should do, a surprising number of people actually do not. And technically there are arguments for both sides, but the most conservative is to just remove any data from a participant that has not given complete data. Here is a visual representation of how this can impact things. So each of these little dots is representing a measurement of some kind, some type of score. And here you can see that these two blue dots, these are the ones who are removed at the different times. And so our average actually goes from 5.71 with these two scores to 4.32 without these two scores. And so it would be possible, if I did not remove this data from here as well, that I would see this mean difference and conclude that there was some difference that happened over time, when in fact that difference is only due to the loss of these two participants in the second group. Because ostensibly they could have just had their similar measurements here and we would have found no difference. When you remove them from the middle of a group, it doesn't really make that much difference. So by popping out these two in the middle here, and not necessarily deleting them from the original measurement data. And now here in the second one, I still have sort of my extremes, and because these two values were very close to the mean, their removal or even addition of scores in that same place does not affect an average or a mean very much. Even in such a case, best practice is to just remove their data from the experimental results. Testing threats. These refer to a change in the participants as a result of taking a dependent measure more than once. This is a type of order effect. These can be managed by either moving to a post-test design only, because in such a case you do not have multiple exposures to the dependent variable, and you could use alternative forms of the dependent variable for pre-test and post-test. This would just include something like using two different metrics to evaluate depression, where you administer one before the experiment and you administer another after the experiment, and that way people do not get better at it. Another example of this would be to try and study inhibition, where you would use a Strube task in the beginning and a flanker task at the end, which are just different types of tasks, and it would prevent you from being able to practice or get better at it. A diagram to show this. So here is just some ability score. So let's imagine we're talking about the flanker task here. For those of you who don't know, the flanker task is a task that requires you to respond to arrows on a screen. Oftentimes you are required to respond to a central arrow that is flanked by 4 additional arrows, 2 on either side. Sometimes all 5 arrows are pointing in the same direction, and sometimes the middle arrow is pointing in the opposite direction of all the others. And your job is always to push right or left, depending on the direction the middle arrow is pointing. Humans, on average, are much faster at responding to the direction of an arrow when all 5 arrows are in the same direction, and we are slower when it comes to responding when it is pointing in the opposite direction of all of the flanking arrows. Nonetheless, if you practice this task for long enough, you will get better and better at this task. So maybe I think some new medication or meditation will help with the flanker task performance, and I have them do the flanker task, and then I give them this new whatever manipulation it is, and then I give them the flanker task again, and lo and behold, their performance is getting much, much better. This could be measured through reaction times or errors. I don't know though if I only have this one group or this one line, whether it is some manipulation I did that resulted in this change, or did participants simply have enough time to practice here that when they did it the next time over, they were just better at the task. Again, in order to solve this, using some type of comparison here helps a lot, because here you can see that the comparison group also increases by a significant margin, resulting, or this gives us the knowledge at least, that practice effects or testing threats of some kind are at play here. If you wanted to remove this entirely, you would probably have to change your design. Notice that even if you change your design, you would still need a comparison group. Next, we have instrumentation threats. These refer to changes in the measurement instrument over time. So a measurement instrument just refers to anything that is used to collect data from your dependent variable. It could be codebooks, self-report scales, it could be physiological measurement EEG devices, whatever it happened to be that's generating the data for your dependent variable. These can be managed in 3 ways. So you can either switch again to a post-test only design, because then you're only using your measurement instrument one single time. You could take steps to ensure that the pre-test and post-test measures are equivalent, meaning you make sure that they're balanced in some way or that they give a certain type of result consistently. And finally, you can counterbalance the versions of the dependent variable measure used, meaning at pre-test and post-test, you give half of the people one form in the beginning and another form at the end, and for the other half of people, you switch this order. This ultimately ensures that you can test if there's some kind of difference in how these two measures impact the actual measurement itself. Now, please note that instrumentation threats are different than testing threats. Instrumentation threats are all about the actual instrument used to measure the dependent variable, while testing threats refer to the participant's ability to get better, or maybe even worse, when they're exposed to a dependent variable repeated times. We'll now talk about combined threats. We'll speak about two of these. One is selection history threats, and this is when an outside factor affects only those at one level of an independent variable. So here what you have is some type of external factor that's affecting the participants in your experiment, but to make things worse, it is only affecting some of the groups in your experiment and not others. This makes it very difficult to know what is causing differences between groups, because ultimately it could have been some random factor that is systematically affecting only some subset of your participants. In a similar vein, there is selection attrition threats, which are when you have some ultimately external factor that results in attrition from only a single experimental group as opposed to across the entire experiment. And further, this is only problematic when it happens in some kind of asymmetrical way. If you're losing randomly people from your experiment across all experimental conditions, chances are it won't be that bad so long as you're careful with managing missing data. But if you have very specific losses in specific groups of your experiment, this can oftentimes cause problems, not only with interpretation of the results, but can sometimes also cause statistical problems in analysis schemes. Next, we turn to observer bias. Observer bias occurs when a researcher's expectation influences their interpretation of the results. Observer bias can impact validity in two different ways. Primarily, it can impact internal validity as it provides alternative explanations for the pattern of results. This would just mean that the difference that we are seeing actually doesn't have anything to do with the true effect of the independent variable, but rather it is the observer's bias that is leading to this difference that we are measuring, and therefore it is no longer attributable to only a single thing, decreasing our internal validity. It also impacts construct validity as it calls into question the ratings given on some dependent variable. If the observer is impacting the interpretation of the results, it might change how accurately some type of construct is able to predict other outcomes and behaviors in the real world, and thus the construct validity of our experiment is called into question. The primary way that this gets controlled is either using double-blind or masked designs. Double-blind studies are those in which neither the participants or observers know what group the treatment is and what group the control is. These are oftentimes used in medical testing or medication testing. In such a case, participants are randomly assigned to one of two groups. Oftentimes the control group is a placebo group to reduce the chances of them knowing which group they're in. And then the people who are administering the experiment are oftentimes not the primary experimenters, and they also do not know which of the participants are in the control and which are in the experimental conditions. This removes the ability to have any kind of bias on the observer's part because they simply don't know which way the groups are and what is supposed to happen. You cannot always hide from participants what it is that they are receiving or that they are in control or experimental groups, and in such a case one can use a mask design in which the observers are the only ones who do not know which groups the participants are in. Demand characteristics occur when a participant guesses what the study is supposed to be about and changes their behavior in the expected direction, or at least what they believe the expected direction is. These can oftentimes be controlled using either a double-blind design or a masked design. So in a double-blind, it should be pretty straightforward. Neither the experimenter nor, or at least the administrators, and the participants know who is in what group and how they're likely to have their behavior changed, and thus it's very hard to modify one's own behavior. Now, in a masked design, Even though the participants know what groups they're in, the observers do not. And this also helps us manage demand characteristics quite well, actually. The reason for this is it is oftentimes the experimenters or the observers who are present at the time of administering an experiment who give subtle cues after watching the behavior of a participant that a participant can pick up on and use to modify their behavior. A real-life example of this is oftentimes in a math class, for example, when you ask your TA or professor if you're on the right track, there are subtle cues on their face that will give away whether you are on the right track or not, and this can be used to modify one's own behavior. To make this even more difficult, oftentimes participants will engage in such behaviors without consciously being aware that they are doing so. Finally, we have placebo effects. Placebo effects occur when people receive a treatment and actually improve, but they only improve because they believe they received a valid treatment. Now, before we go too far into it, it is important to know that placebos are not imaginary. Even though they are not real treatments, they do have real effects, and placebos have reliably been shown to reduce real symptoms, both psychological ones and physiological ones. It is pretty unbelievable, and if that is something that you are interested in, I highly recommend checking out the literature because there are some pretty unbelievable effects, and it is actually very difficult to explain why. These can be controlled using double-blind studies again, because here participants don't know what treatment they're receiving, and ostensibly now everybody thinks that they are in the treatment group of some kind, and you will see that the sort of placebo effect will occur regardless of what group you're in, and differences in now the group systems can be attributed to whatever the independent variable is. When using a placebo, though, there should be a second control group known as a no-contact control group. So in this case, you could have one group who's receiving a true medication, a second group receiving a sugar tablet that looks like the medication, and a third group who has no contact whatsoever with the experimenters to see how they change over time. This allows you to see the impact of the placebo itself, comparing the no contact to the placebo group, and to see above and beyond what difference the placebo has when comparing the placebo group to the actual treatment group. Now, mask designs don't work when you have placebos involved because participants cannot know that they're receiving a placebo, and remember, in mask designs, it is only the observers who do not know which groups are which. Interestingly enough, there is some new evidence to show that placebos work even when subjects are told that they are taking a placebo. So these oftentimes involve people saying something to the effect of, this tablet is a placebo, but there is reliable evidence to show that placebos do actually make a difference. And while these effects are smaller than when participants are not told about the placebo itself, they still can result in positive changes for subjects. Here you can see a difference between a true therapy and a placebo. So here, for example, one second. Okay, here are whatever the symptoms are before some kind of treatment, and here you see after treatment there is a reduction in symptoms, but there is a reduction in both groups, the orange being the placebo and the true therapy being the green, and this difference here is probably the increased efficacy of the treatment group over the placebo, but you can see that both of these resulted in a reduction in symptoms. Now, where a no contact group helps a lot, because it could have just been that this is both related to time. Now, by adding a no contact group, this pink line over here, I can see how much this group is likely to change over the two measurement ratings just being left alone. And this difference now shows how effective the placebo by itself was, and this distance altogether showing the impact of the placebo and the therapy itself. Let's move on into the next section now, where we'll talk about interrogating null effects. So a null effect refers to a situation in which the independent variable did not make any kind of difference or have a relationship with the dependent variable. Now, journals, newspapers, websites, pretty much wherever you find news these days, are not likely to report such null effects because they're not as exciting as effects that find some kind of significant difference. That being said, research with null findings is actually very common, but it tends not to get published very often, and we'll talk about that more on the last slide. When researchers obtain null findings, you'll often hear them say their experiment did not work, but what does that mean? Well, it could mean one of two things. One, that the independent variable really did not have any effect on the dependent variable, and in such a case, the experiment, it technically worked, it just didn't find the results that they were hoping it would find. It showed that there was not really a relationship. Of course, you would have to show it multiple times in order to take stock in those findings, but it technically worked. So talking about it in this way is a little bit strange because it gives away the tremendous expectations that all of us have when doing research to find things that work. And that just goes a little ways to show you also why the bias in publications, both in lay media journals and academic journals. It is, however, possible that the study wasn't designed well or conducted carefully enough, and this is ultimately what resulted in the study not showing any kind of significant differences. And in this case, it would be correct to say that the experiment itself did not work because there's some flaw in the methodology itself. Now, ultimately, however you go about this, it comes down to two different things. Either there's not enough variance or difference between your groups. If all of your groups don't have much difference or variability across them, they're all very close together and they won't look very different, and your statistical analyses will tend to not give you significant findings because most of your groups are clustered together. Another way in which this is problematic is if your groups themselves internally have a high degree of variance. Meaning if your groups themselves have a lot of different individuals within them, it could be that now your groups are so spread apart into and of themselves that even differences between the groups are minimized because of the tremendous variability within those groups. Now, just as a random thing to learn, if you've ever wondered about the F-stat in an ANOVA and what it actually means, well, what it is indicating is the ratio of the between groups variance to the within groups variance. And if you ever have an F-stat of 1, chances are you're not really going to find significant results, but that's just saying that there is an equal amount of difference between the groups as there is within the groups. This is why when you find F-stats that are like 4, 5, 8, 12, and so on, you actually get really excited because those tend to be significant, because we're saying now that 12 to 1 of all of the variance, or a lot more of the variance that we see on all of the data, is because of the groups themselves, the difference between those groups, as opposed to the variance within the groups themselves. If you want to forget about that now, that's totally fine. Okay. One of the things that can cause problems when we have null effects, or what could lead to null effects, I suppose is a better way of saying it, is weak manipulations. And weak manipulations are when the differences in levels of our independent variable are too small or not properly administered. We're unlikely to see effects on our dependent variable. Take, for example, the effect of money on happiness. If I wanted to examine how much giving money to someone increases their happiness, I could probably run an experiment like this. But if I was to set up 3 groups, my no money condition, my low money condition, and my high money condition, and I gave my low $1 and my high $2, I'm probably not going to see so much difference on happiness, because for most people, the difference of $1 here and there is not going to make very much difference. So here's just a diagram to show this. So it is problematic because it reduces the variance between groups. You can see that here where all of the bars are kind of roughly equal height, and we're not seeing much difference across any of them. Whereas if I had made this 0, 100, and $2,000, chances are I would see some more difference between these 3 bars, if in fact money does have an impact on happiness. Insensitive measures are kind of on the other side, and these are if measures used to quantify or generate the dependent variable data are not sensitive enough, then we might not be able to accurately observe differences. For example, if I want to look at the difference in weight by some, or for some chemical reaction, let's say, but that weight only changes by about 0.2 grams during the entire process, and the only thing I have is a scale that is calibrated to the nearest 1 gram, I will never find this difference, well, maybe sometimes randomly, but I will not find this difference because the change that I am seeing cannot be picked up by the measurement tool that I am using. This would be akin to trying to use a regular hand ruler to measure the width of an electron. You just can't do it because your ruler is not sensitive enough to measure such a small thing. Again, this is problematic because it results in too little variance between groups. As you can see here, I could have one group that was, I don't know, 5 and another that was 5.2, and the scale that's calibrated to 1 gram will just make them both look exactly the same. Next, we have floor and ceiling effects, and these are talking about when scores are all squeezed together at either the high or low ends of a measurement tool. When they're all clustered together at the high end, we call them ceiling effects, and when they're all clustered to the low end, we call them floor effects. Here would be an example. You probably wouldn't see this too often, though you'll be surprised how much it actually does crop up. Here, if I was wanting to know how people are feeling in terms of happiness, and I asked them, please rate your mood by circling one of the following. I feel either horrible, awful, bad, or fine. And in this case, either you feel some kind of bad, or you feel fine, or you feel good, but you don't have that option, so you select fine, or you feel awesome, which you also don't have, so probably fine, or ecstatic, which you also don't have, so you probably select fine. And in all of those cases, an entire section of people are all being smushed into this one value, whereas you probably have some degree of play over here. This could happen in reverse too. And again, this is problematic because it results in too little variance between groups. So here would be something like this, where I have just everybody saying sort of this fine. Another way in which this comes about is if I give an exam or some kind of questionnaire that is simply just too easy and everybody is able to score 100%, then if I'm trying to see the difference of, say, taking an exam with pen and paper versus on a computer has any effect, I will never see the difference between the computer and pen and paper exams because everybody just aced the exam, and so there's no way to see the difference. Same thing in reverse. If I did again wanting to know the difference in taking exams by pen and pencil versus online, and I just made a brutally hard exam that everybody got no points on, and everybody was around 0, again, I couldn't see the actual difference between my two forms of administering an exam because no one got any points on the exam, and those two groups again look the same. Ideally, when you are trying to develop measures or metrics, or even if you are looking to use certain measures or metrics, it is important to look at what the average scores are. Hopefully they're somewhere towards the middle of whatever metric you're using, and they have a roughly even amount of variability on both sides of that average. So one nifty thing we have are called manipulation checks. Manipulation checks are just generally a good idea altogether, and time and resources permitting should, in my opinion, always be included where correct or appropriate. Manipulation checks are extra dependent variables that get added to an experiment to ensure that a manipulation worked. And another way of thinking about this is that they help to detect weak manipulations or ceiling and floor effects. So let's say I wanted to know how well people could solve certain types of problems when under high loads of stress or not. And I'm going to induce stress by making people either have a public speaking situation in which they stand in front of 300 people and give a lecture that they've only had 10 minutes to prepare, or I don't make them do this and they simply sit and listen, and now I make them solve problems, and lo and behold, the people who relaxed are better at solving problems than the ones who gave the public speaking. But I would ideally like to know if my manipulation, making them speak in public or not, actually changed their stress levels, which I think is what's causing this. And so maybe not only will I give them the problems to solve, but I will also give them some stress and anxiety questionnaire to see if in that moment their stress and anxiety levels are actually different. If those two things are actually different, then I can safely assume that my independent variable, making them speak in public or not, actually did change their stress levels, and thus differences I now see in their performance could be because of that. If I saw that there was no change in stress levels whatsoever, chances are I'm going to find floor effects. If I see that both groups are really stressed regardless of whether they spoke or not, I might find ceiling effects. Now, manipulation checks ensure that manipulations are strong enough, much like I was talking about just now. They let us know that our manipulations to the independent variable, are actually working. And they also do show us that those independent variable levels are moving or changing in those expected manners. Right? Sometimes people will run experiments, find all kinds of cool findings, and then they'll look at their manipulation checks, which thank goodness they had in those experiments, only to find that their independent variables actually varied in a way counter to what they expected. And so now one has to be able to explain why you found all of these strange results in light of the fact that your manipulation actually had some kind of different impact. And then further, one then tries to understand why that happened. Note that if you did not have a manipulation check, you would have just assumed that it behaved in the way you thought, and one could go on to talk about all of their findings, which could even be significant. And then much later on, maybe somebody replicates the study and adds a manipulation check and then discovers that actually everything didn't work according to plan. And, well, then there's some problems. Confounds in reverse. Sometimes you will find that confounds affect results in a way that hides the effect of the independent variable, and this would lead to an experiment having or indicating null findings, even though you do have some true effect. It's just that your confound that is involved is impacting your results in an opposite or opposing direction to the dependent variable, and this is resulting in the appearance of a null finding. So an example of this would be, is being gifted more or less money going to change how happy we are? Of course, we would expect being gifted more money would make us more happy than being gifted less money. But what would happen if whenever we were given more money, or the people who were given more money, they were given more money by just a super grumpy person, and those who were given less money were given that gift by a really, really kind person? In this case, getting more money probably makes you happier, but the super grumpy person probably bums you out, which reduces that level of happiness. And being given less money maybe doesn't increase your happiness so much, but being given it by a super kind person who's just so nice and sweet is likely to increase your happiness. And this might make both of these groups look the same on happiness, even though the monetary gift was having an impact on that happiness. Finally, we'll start talking about noise. Noise is oftentimes referred to as error variance or unsystematic variance. And one way to look at this would be graphically, so we'll just kind of understand that here. Let me pull up the pointer. So both of these two groups ultimately have the same mean difference, which you can see by the height of these two bars. But you've probably seen error bars like these before, and you can see that these error bars are much wider than these error bars. Chances are this difference here is going to be significant because these error bars do not overlap, while this difference is not going to be significant because of the high overlap of these two bars. Now, the reason for this is because these bars are indicating how spread out the actual data points are around those two means. Here you have a very high degree of variability around the mean, while here you have a very low variability around the mean. And remember, we are also interested in how these two are different from each other, and like I mentioned about the ANOVA, what we're doing is looking at the difference between these two groups and comparing it to how different each of these groups are within themselves. If I increase how much variability is within each of the particular groups, it makes the difference in a statistical sense across the groups seem smaller, because I could have ultimately found most of these findings in either of my two groups, whereas here, not so much. Now, we'll talk about this a little bit more, but ultimately one of the primary things to understand is there will always be noise in data. There's no way to have data that does not have noise, especially when you're measuring human beings. The trick comes from trying to reduce how much noise is present in data. Okay, we'll talk about some sources of noise now. One of the first is measurement error. Measurement error refers to either a human or instrument factor that can modify people's true scores on their dependent variable. It could go up or down. And a couple examples of this. So a human error could be when it's trying to measure length using a ruler, and because of, say, parallax or something, or of how we observe and view things that are fixed lines, it could be that the human records it incorrectly. So maybe something that is 8 meters long gets recorded as 8.2 or 7.2 or 9.7 or whatever. And this would just increase the amount of noise, because note that the true value is 8 meters, and all of those other differences are making it seem like there's more variability within that group itself. For example, I could measure 12 things that are all 8 meters long, but because some of my measurements are for 8.5 and some are 7.4, it looks like there's variability within that group, but there is not, in fact. That variability is just due to the noise of measurement. You could also have measurement error due to incorrectly graded rulers, for example, where not all of the spaces between the ruler are equidistant apart, and so measuring things, let's say, between 0 and 3 inches results in an underestimation, while measuring anything beyond that results in an overestimation. This could lead to additional noise in your data. Another one that many people are actually most familiar with are individual differences, and this just indicates that there are differences across groups that might arise because of people having unique characteristics. So the fact that all human beings are different ultimately contributes noise to an experiment. Imagine a reaction time study. Not all people are equally fast at pressing buttons. Because some people are faster than others, those differences in how fast their reaction times are, some part of the difference is ultimately due just to the difference in how people respond. Now, I hope that I have a roughly equal number of fast and slow responders in all of my groups, but sometimes I don't, and that could result in asymmetrical noise, which can be problematic for interpreting the results. Finally, last comment on the individual differences part, that is not a problem when you're using within groups designs, because it's the same set of people who are in all of your conditions, and therefore fast people stay fast and slow people stay slow, and therefore the individual differences do not come to bear on a within samples or within groups design. This is also one of the reasons people talk about within groups designs serving as their own baseline or having more power. The third source of noise is situational noise. This refers to external distractions. Just imagine that I was running you as a participant through some kind of sort of high intense reaction time task, and halfway through it, all of a sudden my phone starts ringing. Chances are that will serve as a distraction, and for several trials it might cause you to lose your groove and slow down your reaction times, which would make it seem like you have more variability in your response rates than you actually did, but not due to any of the experimental manipulations or your own performance, but rather because I distracted you. This is oftentimes why many experiments are performed in very specific settings. It does also raise into question many of the findings that are generated from things like Amazon Mechanical Turk, because there is no way to know what environment each of those MTurk workers are in when they take whatever study is being administered to them, and there is no way of controlling or managing that noise in a systematic way, because not everybody who takes them is living in the same house with the same dog and the same furniture and so on. Ways to manage noise. Well, you can measure the DV in very precise and careful ways. Oftentimes we do this using established or calibrated tools, right? We don't make our own rulers. We go by graded rulers. We don't just randomly make up new questionnaires. We use questionnaires that have been validated or established. That cannot always be done, and if such tools are unavailable, one way to get around it is to just measure more people. By measuring more people, yes, we continue to have noise in our system, but so long as that noise is random, by having enough people, we will ultimately average that noise out. This is one of the primary ways in electrophysiology work how ERP studies are conducted. Hundreds and hundreds of recordings are made and averaged together to look at what the underlying signal is, because if you only look at a single one, it just looks at noise. Now, increasing the number of people you're measuring will generally not work to manage this problem if your noise is symmetrical or it's impacting in a specific direction. Now, we would generally no longer call that noise anymore because that error is not random and it would fall under some type of sort of threat to internal validity. Another way of dealing with this is to very carefully control the experimental environment, and you probably just want to do this anyway if at all possible. And also please note that all of these can be combined. The last way is to increase the manipulation of a study, and this means that you make the difference between your independent variable levels even more stark or more drastic, because then even if there is noise in a study, if you have a huge difference, that noise is not going to have very much of an impact. Lastly, we'll quickly go over power. So all of these things around noise that we've been talking about, both the results or causes of noise and how it impacts our data and how to manage it, ultimately fall under the rubric of power. And power falls under statistical validity, and it refers to the probability of correctly rejecting a null hypothesis where there is a true effect. So basically, did you reject it properly when you should have? Now, you can play with this graphic at this website here, and it will let you move around the actual power or alpha level or number of participants or even the effect size itself, and it will just show you visually, let's say, how that will look. So here you can see there's a Cohen's d of 0.44. That is just indicating the difference in the two heights of these hypothetical peaks. This would be your null distribution. This one here is your alternative distribution. This sort of orangey section here is half of your alpha. This is that rejection region we find. Here we're saying at HA is the actual statistic that we found. Now, because it is lying over here, it falls in the tail of our original null distribution, and so we would reject it. Now, here is where power comes into play. Anything from that point of rejection, for where the tail of the original null distribution starts, if I draw a line up, and now imagine everything in this distribution from there on out, when I find it, I'm of course assuming it's from this distribution, and I correctly reject the null hypothesis. So this over here will give me the aggregate proportion of the time I will do so correctly. But note that I could technically belong to this distribution and get a value somewhere in this dark blue region. Now, if I got a result here, technically I am still part of this distribution, so there is a true effect. But I would not call these significant because these are not within what is defined as the tail of my null distribution. And in all of these cases, I will fail to reject the null hypothesis even though there is a true effect. So in this case, this diagram here is showing you what 80% power looks like, meaning 4 out of 5 times I will correctly reject the null hypothesis. This type 2 error rate is oftentimes called beta. It is 1 minus power, and you can swap those around. And so it's showing us 20%, meaning 20% of the time we will fail to reject the null hypothesis even though it is true. Fail to reject even though we should have. Yep, and finally, type 1 error is just oftentimes associated with your alpha level. I highly recommend going and playing around with it, even though that won't be something that will be on your exams. Last, we'll talk about null effects. So we've talked a bunch about why it is that an experiment might have failed to find significant findings, but sometimes there are just no effects to be found. And when that is the case, these are called null effects. Now, while null effects can be published, they're often published much less than significant findings, and this is primarily due to most people just being more interested in independent variables that work than those that do not, and that for obvious reasons. It also has a huge effect on the impact factor of an academic journal. So the impact factor is what defines how prestigious a journal is, which of course impacts how much they can charge for their journal. But anyway, an impact factor is determined by how many times articles in their journals are cited by other academic papers. So the more times they get cited, the more their prestige or impact factor increases. And tying that to the first point, the more significant findings that are published, the more likely those are to get cited because people will use that work to build on and do other work. And so those automatically get more citations than null findings, which didn't work. And therefore, there's a strong incentive from publishing houses to publish significant findings over null findings. And this is actually seen a lot in current literature. That being said, if a study is adequately powered, meaning you have really, really good power distribution and you're able to correctly and incorrectly sort of sort out what belongs in what distribution, then even having null findings can be very informative, right? Just imagine if you were working on something incredibly complex and time consuming and it meant a lot to you and you spent 2 years doing the work on it, and after 2 years of careful study and deliberation you finally get your results and they're not significant. Now, of course, you lament about this, you take a couple of colleagues out for a beer because you've just basically spent 2 years of your life for something that didn't work out. And as you're telling your colleagues about this, they're like, oh yeah, we tried that a few years back and it didn't work either. Imagine how you would feel there. You could have been saved from so much heartache if you had known that other people have tried whatever it is and it did not work. By not publishing null findings consistently, we have people who spend an inordinate amount of human work hours redoing things that are already technically known not to work, but no one has access to that information because mostly those don't get published, and so they just stay in the drawers of academics, and that is where the term file drawer problem comes from. That there are many studies that have been worked on but never published that just sit in the drawers of academics and therefore do not contribute to our collective knowledge. There is some push in today's world to start changing this, but it is still a huge problem that many of us are still struggling with to this day.